Dr. Kohli and Dr. Korde for arranging all these lectures. And today I will speak about the advanced functional materials for energy applications. And from this lecture series, I can see that a lot of people they are speaking about the energy storage, supercapacitor, a lot of things, advanced functional materials, technologies, all these things. Okay, but I will focus on basically on how to make the materials, how to characterize them, and how to apply for the applications. Like I will show one of the example. Like if time permits, then sodium ion batteries, one of the emerging area. So this is maybe a interactive session. First, I will talk about the work which I have done in last 25 years. Then I will go to the recent work which I am doing now. So how many people are available for interaction? Means when I will ask some question, then they have to respond because it's not one way traffic. Okay, it's not like I will speak and you will listen because I know that online lectures are not good. Only maybe 10 minutes or 15 minutes you can listen very carefully. Then afterwards nobody will listen it. Okay. So for that purpose, I would like to interact with all the participants. So I can see only 15 participants online here on this Google link. So how about other people? Am I audible?
Yes, sir.
Okay. How about how many participants are online now? Oh, okay, fine. So yesterday I came to know about 300 or something. So just I wanted to make sure. Okay. So all of you are from college teacher or some institute or university or IIT faculties are also there from Pune and outside, right? Okay. So how many of you have the research backgrounds? Means a doctor or something, you have done PhD or something? More than 50% or almost all? Okay. Or doctor. And remaining are just say NET or all qualified. Okay. So maybe they are also interested in research or something. So rather than giving the hyper lecture, what I have done or something, it's good idea to give a knowledge about the how to do research, right? Rather than giving uh, more detailed or hyper or something physics or something. Okay, basically this is material science, not physics, not chemistry or something. This is only material science. Whenever we want to go for some application, technology application, material is very important. Okay, so let me speak about my institute first. So this is very nice campus. This is developed in 2.2 acre of 200 acre of the land. Okay, so the area is about 2.2 kilometer, and most of the part is covered under forest, and 50% of the land is only available for construction. And these are our building. This is a main administrative building. Just make me pointer. This is administrative building, and this is our, we say it's a resource center. Basically, the library in your terms is library. And these are the academic pods: physics pod, chemistry pod, then computer science, mechanical engineering, civil engineering. So these one pod is located for one department. And backside of this area, these are the hostels. Now we have 5 hostels, very big hostels, and more than 600 students they are staying in one hostel, and we are giving one separate room to everyone. And more than 178 faculties are recruited. Now maybe in last term also some recruitment was there, so it's more than 200 faculties now, and staff more than 250. Okay. So our institute was ranking 10 earlier, but now last year it came down because of this pandemic and all these things. Is 14. Its ranking is 14 among the more than 1,000 institutes all over India. So we have now 21 faculty members in our department and postdoc members and more than 300 students. They're studying in the BTech, MTech, PhD courses. And this is my current research group. This is myself, and this is Arjana. She is working on sodium and batteries. This is Abhishek. He's working on solar cells. This is Manish. He's working on gas sensing. And this is Dr. Subhash. He's recently completed PhD on perovskite solar cell and is moving to Japan now. And this is Gina. He's working on theoretical and computational and experimental work on sodium and batteries. So our area is diverse. A lot of topics are there, and they are working on one topic. And if somebody want to collaborate with us, then you are free. Also on 22nd and 23rd, we are organizing India Japan International Workshop. You want to participate in that, then you are also welcome. So this is my research alumni group. This is more than 17 students they are completed, and they are working in the various part of the globe: USA, UK, Germany, South Korea, Japan. Okay, a lot of things are there, and currently 6 students that they are working. 16 PhD they have completed, and 6 are working, and more than 40 MTech and BTech they have completed there. And we are always busy in organizing some courses. So this is in 2016 we organized some GAN courses, and this is Professor Akira Iwo. He was my host during my JSPS fellowship, and he was here for talking about the high pressure synthesized materials. I think nobody knows about this high pressure synthesis technique. This is one of the preparation technique which is used for very focused research work. For example, if you want to make a diamond or jewelry materials in your lab, then it's possible. From carbon, we can make a diamonds, and I used to make diamonds in the lab. So this is for that we need very high temperature and high temperature pressure. Okay, so not only that, when we want to invent the new materials, when we go to the interior of the earth, lot of temperature and lot pressure is there. Because of that, we can get lot of new things, variety of the materials, minerals, and all these things. Okay, so why that is happening? That the to address that, this high pressures and this technique is very important. Okay, and this is Professor Neri. He is the grandfather of the sensors. In 2016, he visited to our institute and delivered lecture on the chemical sensors, starting from principles, technologies, and applications. And very nice lecture series that is still available online on MHRD, both lecture series. Okay, and many of maybe you are knowing about this faculty. Okay, this is Professor Sulba Kulkarni. She was working at earlier Savitribai Phule University, then CIMET, then ISCR Pune. Now she is retired. Okay, and she visited here to give lecture on some short-term course on energy materials and applications. And this is Professor Kim. He's from Gangnos Technological Institute, South Korea. He also delivered some lectures on the solar cell in the GAN. Basically, he's expert in the solar cell. Okay. So these are my research activities. Advanced functional materials research group, really advanced. It's not only by name, only one material or something. So basically, we focus on the superconductors, ranging from different type of superconductors, like Kuiper-based superconductors. Maybe many of you don't know about this, what I'm speaking about, but superconductors, I'll talk a little bit about that one in later section. These are basically iron-based superconductors, copper-based superconductors, alloys, metals, all these are superconductors, okay? And I am focused on iron-based superconductor and copper-based superconductors. So I'll talk about something about this one. Then energy harvesting. Energy harvesting nothing but we have to generate some energy. There are different techniques. We can use solar cells, which can convert the. What is solar cell? How many of you know about solar cell? You can speak. I cannot see your hand rising. You can unmute and you can speak. Anybody knows about solar cells? Nobody knows. Solar cell is a device which convert solar
Which
energy into,
converts the solar energy into electrical energy.
okay, by using the semiconductors, PN
Right.
junction or something. Okay, but this also has a lot of generations. For example, silicon solar cell, thin film solar cell, perovskite solar cell, okay, or Dyson solar cell. Different things are there. Then piezoelectric materials. So our focus is on this solar cell, and we are working on the all three type of solar cells, and then piezoelectric materials. Now this is very important. Piezoelectric. Piezoelectric means mechanical energy into electrical energy. When we walk or when we do some exercise, then that mechanical energy can be converted into electrical energy, and that can be utilized for various purposes like the regular applications. So for this, we are using the polymers, and if we apply the pressure on the polymers, then that is converting the electrical energy. So this is a signal of whatever the device we have made, and by using the palm, then we can convert that mechanical energy into electrical energy. And most of the tracks in the Japan, they are using this piezoelectric materials to give the signal to the trains. Okay, so this is another one. Now we have generated the energy. Now we need to have the materials which can store the energy, right? So for that, batteries and supercapacitors. Batteries from 1980s, sorry, in 1800 years, the batteries were invented. Then the technology went on, and in 1980, basically whatever the lithium and batteries we are using in our laptops and our mobiles, that develops. Okay, but now lithium ion is very expensive and is very costly, explosive, and all these things. So we need to find out the option for that because resource is very limited. So the work is going on sodium and batteries. So that I will little speak about this sodium and batteries, why they're important, and what are the drawbacks of the current lithium and batteries, and how to fabricate sodium and batteries. About this one, okay. Then a lot of people they are speaking about the supercapacitors. Okay, this can charge in 10 seconds or 20 seconds. This is very good to speak about. It will charge in 10 seconds, 20 seconds. But really, this is not good because the supercapacitor only for the fancy word. But in order to make this capacitor, it's very difficult. We have to use large area. We have to use large amount of quantity of the materials to store this energy, and this can deliver energy for short duration. High energy, but short duration, very short duration. Okay, so a lot of people they are saying about we can make 1,000 Faraday, 100 Faraday, or more than that. Okay, but this is only lab scale. When we go to the real applications like in Singapore or somewhere, the buses are using the supercapacitor and batteries together. So such type of devices need a lot of fundamental work and technological work. Okay. So next topic which I am working is sensor. Why we need sensor? A lot of type of sensors are there. Temperature sensor is there, then gas sensor is there, chemical sensor is there. Basically, in our environment, we have a lot of type of this greenhouse gases: carbon dioxide, carbon monoxide, nit NOx, ammonia, ethanol, methanol, all these things, industrial waste also. In order to be a safe from that, we need to have a sensor. In order to control the indoor quality of the air, the sensors are very important. Okay. So for that purpose, my research group is working on developing ammonia sensor, room temperature ammonia sensor, then ethanol sensor, CO and CO2 sensors, and which materials are good, how to sense it, how to characterize it, and how to bring to the market. Okay. So all type of this type of work we are doing in our research group, and Professor Neri us to develop this technology. Okay. And beside this, we are also working on the magnetic nanoparticles. We can really make a 1 or 2 nanometer nanoparticles, and we can utilize this for the drug delivery, for controlling the antibiotics and all these things, sun cream, all these things. We are using that magnetic nanoparticles. And besides this, we can know the basic properties of the material, fundamental terminology of the materials. So we are working on that part also. So this is the home built our setup for measuring the gas sensor, and this is all developed by our students. We are not uh, getting from any vendors this thing. Okay, so all these IIT made, IIT students are made. Professor Dr. Alpa Sharma, he was working on this one and he developed. Now he's working in some university in Odisha. Okay, so this is a humidity sensor. How much the percentage of the humidity in our atmosphere? Then this is a gas sensor setup, and how to measure the gas sensor and all these things, how to calibrate it, that I will tell about the later section. Okay. So this is our home built setup for the humidity and gas setup, sensing setup. So little bit I will speak about the superconductors. How many of you know about the superconductors? Are you teaching some superconductors to the students? You teach only about the metals, semiconductors, and insulators, right? So that is in your syllabus, right? Perfect. You need to read and you have to teach. Okay. So this is I'm giving you ready-made things. Okay. So what is the basic property of superconductor?
रजिस्टिविटी हाई होती है.
No. Sorry. Resistivity zero. Okay. Another property only zero resist.
हाई कंडक्टिविटी हाई होती है सर.
Conductivity is very high. Okay. So in short, this is the material which shows very interesting phenomenon. Okay. Basically, when we have to cool down to liquid helium or liquid nitrogen range, then its resistance becomes immeasurable. Okay. We are not able to measure any more resistance of that material. So that we say is a zero resistance. Okay. So DC electrical resistance is zero. I'm saying DC electrical, not AC. Okay. DC electrical resistance is zero, and it shows diametric in nature. Now, how to know that this material is superconductor or metal? Okay. So Professor Kamerling Moniz in 1911, basically in 1908, he was trying to make a liquid oxygen or liquid helium. Okay. So that time he was using the stirrer of made by using this mercury. Okay. And while stirring that compressed gas, he used this mercury stirrer. Basically, mercury is liquid, right? But when we cool down to very low temperature, it becomes a solid. Okay. So while doing that, he was interestingly measuring the electrical resistance of this mercury, and he found that at 4.2 Kelvin, the resistance of this mercury drops from 0.1 to 5 ohm to 0 ohm. Okay, immeasurable, 10 to minus 5 ohm. Okay. So this phenomena is given superconductor. Normal conductors are there, but this is superconducting because this is showing the zero resistance at particular temperature. So the name was coined as a superconductor at that point. Okay. So for this, he got the first Nobel Prize in the field of superconducting. And superconductor is the only one field which got 7 Nobel Prize for different inventions. This is the only, and this is more than 100 years research work is going on this one. Okay. So now, how to distinguish superconductor and metal? So can you see this figure? X-axis is temperature, y-axis is resistance. Okay. And this is superconductor, and this is metal. For example, we consider this point as a 300-degree Kelvin, and we are cooling down to 0-degree Kelvin. And when we cool down this, for example, this is a gold. Okay, we are cooling down to very low temperature, and at even at low 0 degree Kelvin, this is showing some resistance. Okay, do you know what is this resistance and why this resistance is appearing here?
सही ये फार्मूले से आएगा ना होता है आर नॉट इक्वल टू 1 प्लस आर नॉट अल्फा डेल्टा टी
But
ऐसे
that
करके
is okay. Textbook matter is okay. I'm not teaching any textbook. I'm not going details of the textbook. Okay. What is this? What is physical
डिजिटल
significance of this R0? Why this is showing? This is very important thing, right? We have
एट
to
एट
think
जीरो
about.
टेम एट 0 डिग्री केल्विन पर इसका जो रेजिस्टेंस होगा मेटल का
Huh, but why that is there? That's the question. We teach to our students. Okay. In case of semiconductor, this is like this. Okay. We have some experiment to conduct the band gap by using the semiconductor. We have to heat, then we have to cool down. Okay. Then the slope of that resistance and temperature that give the slope. And by using that slope, we can calculate the band gap of the material, germanium, right? So that all these things we know that BTech first year or B first year experiment maybe you are conducting. Okay. But I'm asking why this R is not zero. It should come to the origin, right? The resistance and temperature. When the temperature is zero, it should meet at the origin because this is conductor, right? We expect that when the temperature lowering and it should meet at the origin, but that is not happening. Rather than meeting at the origin, this is meeting on the y-axis at R0. Okay, this R0 is nothing but called as the residual resistance, and no metals is perfect. No metal is pure, perfect or pure. Okay, we say it's why because there are some impurities, some defects are there. Even that material is pure, some defects are always there. And because of that, this shows a resistance. And that resistance at 0 degree Kelvin is called as the residual resistance. That resistance is called as residual resistance. So this may be different for different materials. This slope may be different for different materials. For example, mercury or no, mercury superconductor at low temperature, lead or gold or copper or silver. Okay, they are different. They have different slope, different resistivity, and they meet at different points. But still, they are not 0 at 0 degree Kelvin. But when we cool down superconductor up to certain point, they follows the nature same like the normal metal. But at particular point, they loses their resistance and become the resistanceless state. Okay, so the temperature at the materials become the resistanceless state. That temperature is called as critical transition temperature. Okay, and the materials they are called as the superconductors. You can see the slope of this superconductor and metals. They are almost same. Okay, but at particular point, the superconductor loses the resistance and become the resistanceless state. And the point starting and ending, they are this is called as the transition superconductor transition width. Okay. So superconductors are the interesting materials. For certain materials, electrical resistance. This electrical resistance vanishes and becomes immeasurable at low temperature. The temperature is liquid helium or liquid nitrogen range. Okay. So what is the temperature of the liquid helium? Do you know what is the temperature of the liquid helium? 4 Kelvin. And nitrogen 77 Kelvin. Right? Maybe a lot of your lab experiments you are using that nitrogen helium. Beside that, we have also liquid oxygen. Do you know liquid oxygen, liquid hydrogen? How much is the temperature of liquid oxygen and liquid hydrogen? Any guess? I want response from you quickly. No. About which one? Liquid liquid oxygen, how much? Tell me in Kelvin. liquid oxygen, it's 90. Okay. In case of hydrogen, it's 20. Okay. Okay. Move to next. So this is the first property, right? Electric resistance 0 in case of the superconductors. Then second is magnetic property. We'll take three materials. This is normal metal, then this is perfect metal, and this is superconductor. Okay. In case of normal metal, take this normal metal, then cool down to very low temperature, like for example 4 degree Kelvin or something. Then apply the magnetic field, or apply the magnetic field, then cool down. So irrespective of that, if the magnetic lines are passing through that materials, they will keep on passing. Okay. So first you cool down or apply the magnetic field. If you apply the magnetic field, then magnetic lines will be passing through that. Okay. So this is normal metal. But in case of perfect metal, that depends on when you are applying the magnetic field. For example, you are taking this perfect metal and cooling down to very low temperature at 4 Kelvin, then apply magnetic field. Then partially these magnetic lines will be deviated, reflected. Okay. So it means they are called as the weak diamagnetic conductors. Okay, weak diamagnetic conductors. Maybe in Kittel book you can easily find out this definition. Okay, maybe you are only heard about the weak diamagnetic, but what is weak diamagnetic? Means when you apply the small amount of magnetic field that can reflect, but when you apply the large amount of magnetic field that can pass through that material. Okay, so at low temperature, if you apply magnetic field, then that can reflect from that material. And when you come to the original state, again that becomes the normal metal. Okay. But in case of perfect conductor, if you are applying the magnetic field first, then you are cooling down, then what will happen? You can see this clear difference. The magnetic lines, they are passing at the initial stage, they will keep on passing at the even low temperature at 4 degree Kelvin. Okay. And if you remove this magnetic field and bring back to the original state, then you can see the eddy currents are developed inside this one. Perfect metals. Okay. Okay. So this is a basic difference. Normal metal, magnetic lines are always passing, irrespective of you are applying magnetic field and cooling down. In case of perfect conductors, if you cool down then apply magnetic field, then partially it will be reflected. But you apply the magnetic field and cool down, then all magnetic lines will be passing through that one. But if you come to the normal state, you have the eddy current. Okay. In case of superconductor, this is a metal. This is superconductor. Okay. Cool down to very low temperature, then apply magnetic field. What is happening? All the magnetic lines, they are deviating. They are reflecting from that. Okay. Means they are pushed back from that superconductor. Okay. So if you apply the magnetic field and cool down, so what is happening? Again, the magnetic lines, they are repelling from that material. Okay. So this superconductor cool down to very low temperature at 4 Kelvin. And irrespective of that, whether you're cooling down and applying magnetic field or applying magnetic field cool down, all the time these magnetic lines are repelling. Okay. It means this material is diamagnetic in nature. The applied magnetic field and developed magnetic field inside a superconductor, they are equal and opposite. So that is called as the diamagnetic in nature. Okay. So when we bring back to the normal state, they behave as a normal metals. Okay. So this is the basic difference between normal metal, perfect metal, and superconductors. Okay. So when we said superconductors are materials, then that material should show two basic property. What is first one? What is first one? DC electrical resistance should be 0. Second hallmark is superconductors are always diamagnets. Okay. So when we want to characterize these superconductors, that superconductor must show both the properties. Okay. This is the way how you should teach to your students. Okay. Now we have this property of the Meissner effect and all these things. So what are the applications? Why we need this? If it's leviating something, then we should use this for some applications, right? So for that purpose, this is Meissner effect. This was discovered by Meissner and Rochefeld in 1911, and you can Just the minute I will play this video, and I'm not sure whether you can hear the. Okay. So basically, this is superconductor, and the rotating on the top of that was the magnet, and this is cooled down to very low temperature. And if we use that magnet and keep on rotating, that will be in rotating direction. Okay, that will be always in the rotating thing. Okay, so the magnet is magnet is levitating on the superconductor, so that's called as the magnetic levitation. And by using this property, we can use in different application. I will tell one of the application later section. Okay. So the levitation is so much strong. If we put our hand or something in between that superconductor and magnet, that will not disturb. You have seen already glass and hand, all these things. Okay. This is a very strong magnetic lines. They're passing through that. Okay. So this is also called as the quantum locking of the magnetic lines of the superconductors and that magnets. Okay. So this was first discovered in 1933, and this is can be utilized for some applications. Okay. So this is the application of that magnetic levitation. So bullet train, basically this superconductor and magnetic tracks. This is superconducting train, and tracks are made by the magnets, and that will be always having the north-south poles. And when this train runs, then that poles automatically changes, and that train leviates. That has a gap between this track and this uh, train. Okay. So the important thing is here is that there is no direct contact of the road with this device or this vehicle. Okay. And as a result of that, there is no friction. When we use our road, there is a friction of the tires with our road. Okay. So that is the resistance that will kill our speed. But as there is no direct contact of this device with this track, so this can run with the speed of bullet. Okay, that's why it's called as the bullet train. This is called as the magnetic leviator train, or this is also called as the magnetic leviator train. Okay, and this will run with the speed of 500 kilometer per hour, and this is being tested in Japan, and this is in regular use. And recently, in 2025, the track between Tokyo and Osaka that is connecting, where the trial is going on, and that will run with more speed than this 500 kilometers per hour. One of the example that by using these superconductor trains or magnetic leviator train or bullet train, in India, where is the bullet train construction is going on? Do you know bullet train construction is going on? That is not magnetic levitated train, but that is bullet train, high speed train. Do you know where is that? Where construction is going on? You have to interact, okay? Keeping quiet is not good. You have to interact. It's between Ahmedabad and Pune. Modi had announced this one 3 years back. And recently I visited Ahmedabad, and really that station is ready in Ahmedabad, okay? And bullet train track is being constructed from Ahmedabad to Pune. And that speed will be about 350 kilometer per hour, not 500 kilometer per hour, okay? And morning, the person from Ahmedabad can reach to Pune. After doing all his marketing and all these things, he can go back to Ahmedabad, okay? So that is the purpose. You want to make the commercial hub Pune, okay? So the distance between Delhi and Mumbai is about 1,500 kilometers. Okay. Then, if you want to drive from Pune to Pune to Delhi or Mumbai to Delhi, how much time it will take by considering this 1,500 kilometers? Any idea how much time it will take by car? Are you able to hear me? Am I audible?
30 hour near about, sir. 30 hour.
It's about 30 hours it will take, because we are using 70 kilometers, 60 kilometers, 80 kilometers, all these things. Okay. So that will take about 1 day or more than 1 day. Okay.
Yes.
So if we use a plane, for example, from Pune to Delhi, we consider this distance is 1,500 kilometers. How much time it will take from Pune to Delhi? The flight?
2 hours.
2 hours, right? So from your hometown, from your home, you need to go to airport. That will take 1 hour, right? Again,
Yes.
waiting hour is 2 hours.
Boarding. So time with
Um,
that.
that waiting hour is 2 hours. That's compulsion, because 30 minutes early you have to 90 minutes earlier you have to reach there. Then once you land to Delhi, Delhi airport is also outside the Delhi. Okay, it will take one hour. Okay, so basically you are reaching 6 to 7 hours, right? Yes or no? Six to
Yes, sir.
seven hours. Okay. So where is the railway station in Pune? Is center or outside?
At the center.
So how much time it will take from your home to that? Hardly 30 minutes,
Yes,
right?
sir.
30 to
Yes.
40 minutes, depending on the traffic.
Yes,
Also,
yes.
the station inside Delhi, also that is inside the city, right?
Yes, yes, sir.
So that will be 30 minutes or something. So if train runs with 500 kilometer per hour, the 1,500 kilometer distance from Pune to Delhi, that can be covered in how much hour?
Approximately 2 to 3 hours.
2 to 3 hours, right? So which is
Yes.
easier? Also, the train tickets are they are cheaper compared to the plane ticket, right?
This
So,
technology is
hmm.
good.
So this superconductor magnetic levitated train, this is very advantageous. For this is brilliant example, and this can save a lot of time, economy, energy, lot of things it can save. Okay, because only what we need, the superconductor train, and if we bring the material to room temperature superconductor, that's excellent. So this
Yes.
is one of the application of the superconductor. This is used for the transportation. So second example of the superconductor application, this is energy saving. Okay, this is related to energy. That's why I'm telling about this one. This is energy saving. In order to use a normal coal or hydro thing or electricity, a lot of things is there. So that will also take another 18 hours or something, but that's not good. This is only superconducting trains. Also, superconductor, if we use the superconductor wires, then once you pass the current through the superconducting wires, the current in that superconductor will not die for millions of years unless and until you'll change the physical properties like temperature, pressure, all these things. If you keep constant, then the current flowing through that superconductor that will not die. Okay, it will remain as it is for millions of years. This is the basic property of the superconductor. Whatever energy is present in that superconductor, that will remain as it is for billions of years. Okay, so this is another basic property of the superconductor. So that is very important property of the superconductor. Okay, so these are the few models that's being utilized in the Shanghai, China, and all these things. I visited there, so that time I took some photographs. So these are the photographs of that one. Okay. So another application is that if we use this, then what will be the situation in maybe 2050 or something later section? Okay. So just I will play some video, then we can imagine that how will be the our future. Okay, you have seen that if we can make the superconducting car and construct the roads of magnets, then there is no friction. So car can run also with the speed of 500 kilometer per hour, and there is no possibility of the accidents because the height of the cars can be adjusted, and on the same track, multiple cars can be driven. Okay, so in future maybe all the flying cars will be there. So that era will be coming soon because now we have a ML and AI. So that thing will really come depending on superconductor thing. Okay, so this is another example. Then another example is in power transmission. The superconductor is very good. As I already told that once you pass the current through that material, that will not die for millions of the years. This is the basic property of the superconductor. Okay. So currently we are using copper wire or aluminum wire to transport the energy from generator to real appliances, right? Somewhere may near maybe in Trombay or somewhere that energy is generated nuclear power plant. Okay, that is being transported to the Pune. Then we what type of cables we are using? Aluminum, right? Aluminum cables are we are using. Okay, and when we pass very high current or high voltage through that, that is being heated. Why that is being heated?
Resistivity of material.
Because of the restorative material that's called as Joule heating. Okay,
Yes.
and because of that, the flow of the ions of flow of the current that is blocked. Okay, and
Block.
20% of our energy, whatever we are generating, that will be wasted. 20%, not less. 20%. Okay, this is huge loss. But if we can use the superconductor, there is no resistance. So whatever the energy we are generating at the generator, that will be transmitted to the real appliances. Okay. So there is no loss of the energy. So this is one type of energy saving thing. Okay. So this is a very potential for an industrial revolution. And whatever we are generating the power at the generator, that can be transferred to the real appliances. Okay. So this is very good example for the power transmission. And superconductor, there is no power loss because no resistance, no heating because there is no resistance, no fossil fuel utilization, no coal, nothing is there. So no evolution of the greenhouse gases. So there is no pollution. So this is called as the green energy. This is called as the green energy. And lot of magnetic energy savers are there by using the superconductors that is being implemented in USA and all these things. But basically in our India, a lot of not so much work is going on here. But when I was in Japan, so we have really developed a lot of materials which are superconductors. Okay. So we have seen transportation, We have seen power transmission. Now, what is important? Who is your good friend? Do you have good friend? Participants, do you have good friends?
Yes, sir.
Yes, sir.
Yes,
So who is your good friend?
there's so many.
So many.
Wrong question, wrong answer.
जो
Your body
हमारे
is your
काम है
friend.
सर.
Your body is your friend. No one is your friend. Okay. In order to protect that, you have to diagnose your body. Okay. You have to keep your body healthy. So nobody is your friend. Only your body is your friend. Okay. So in order to diagnose that body, you need applications. Okay. So everybody knows about the MRI, but how is made and what are the applications that you don't know, right? For example, some nervous system is not working, then some laziness is there, or so you're falling down while walking. Okay. So that is because of the failure of the nervous system. The blood is not reaching to your brain is not working properly, whether that is tumor or cancer is there in our body. Okay. That can be scanned. Okay. In order to scan, we need a very sensitive detector, and that detector is called as sensor. That sensor is made by this magnetic resonance imaging. Okay. So this magnetic resonance imaging works on the superconductor insulator superconductor junction, and it can detect very small magnetic field. Okay, very small magnetic field. So can you guess, in our body, do you have a magnetic field? Do you have magnetic field in your body? Do you have magnetic field in your body?
No, sir.
Yes.
Somebody said yes. Somebody has said no.
Yes, yes है.
कहाँ पे होता है magnetic field?
ब्रेन में.
कॉन्फिडेंट नहीं है. बोल तो सही रहे हैं पर कॉन्फिडेंट नहीं है. ओके. So we have a magnetic field in our brain and our heart. Okay.
Okay,
And
sir.
how much is magnetic field? 10 raised to minus 12 Tesla. Very minute magnetic field present in our body. Okay.
Okay, sir.
So in order to detect that magnetic field, we need to have a sensor that is more sensible than more uh, what we say in our CGS unit or something list count. Okay. So this MRI can detect of the order of 10 raised to minus 14 Tesla, two order more less magnetic field than whatever magnetic field is present in our body. And by using this MRI, we can scan our body and detect the tumor and cancer present in our body. So is it good application of superconductor or not?
Good application, sir.
So in this, we are using liquid helium and liquid nitrogen. So I given three applications of superconductors. Maybe before this, you are not aware of the application of superconductors, not went through so much things, okay? But really very interesting applications. One is transportation. We can make a superconductor trains, and that is really working in the Japan and other countries. Okay. Second things, in USA they are using the superconducting cables to transport the energy. In our India, we are using the laying down all the cables above the earth, but they are underground in USA and Japan and other things. Okay. And this is third application, medical application. Okay. So this will detect the very minute magnetic field present in our body. Also, it can interact with the hemoglobin and map the things that can detect the tumor. Okay. Hemoglobin has the iron, and iron is magnetic sensitive. Okay. That we have to know. Okay. So these are superconducting single crystals which I have grown in IIT Indore. Okay. And this is very flat. And now we have to characterize this by using different techniques. XRD, then TM, lot of things are there. This is magnetic measurement, and this is electrical measurement. I said that the material should show zero resistance. So all these materials are showing zero resistance, but very low temperature. Okay, about 7 degree Kelvin or something. This is showing. Okay. So how many of you are doing the basic research? For example, when you prepare the material, what type of correction you do?
Zero resistance.
First, you prepare the material, right? Some different technique. For example, you are using the chemical bath deposition or by Saloster reaction method, some other techniques. Okay. If somebody is not understanding, then please tell me. I will explain what is that. Okay. This is not about talking about my research. If I can give you something, then that's more precious than whatever I'm talking about my result. Okay. First, we have to prepare the material, and for that, we have some techniques: chemical technique, physical technique, or electrode deposition technique. A lot of techniques are there. So, I'm not going so much details, but I will give one example that chemical bath deposition technique for the nanomaterial synthesis, if the time permits. Maybe I think it's almost 50 minutes now. Okay, and another 1 hour is there. So, I will just highlight some few results. Okay. So when you prepare the materials, the first gradation you have to carry out is XRD, X-ray diffraction technique. And that will give the information about the material purity, phase formation. Okay. Then you can determine the lattice constant, all those things, and whether doping is happening or not, that you can detect. Okay. Understood? So whether that is polycrystalline, single crystalline, all these things you should know. This is single crystalline XRD. Okay. Why I'm saying this is single crystalline XRD? The peaks they are appearing are only 00L. Okay. Maybe HKL is there, right? Miller indices HKL. So this is 00L. Okay. And they are appearing at equidistance of the 2 theta. Okay. So when this type of pattern happens, this is called as the single crystalline nature. Okay. On the other hand, if you see a lot of peaks and they are indexed with different HKL, they are called as a polycrystalline material. In case of amorphous material, you will not see any peak. Okay. So that is the basic difference of the amorphous, polycrystalline, and single crystalline materials. Okay. This is just highlight. Okay. So many people they are working on the nanotechnology, and little bit I'll speak about the nanotechnology. What is this and why we need this? The design, characterization, and application of the different structures, devices, and systems by controlled manipulation of the size and shape of the materials. Why we need to control this one? Because we need to control the property of the material. How we can control? If we can control the at the atomic scale or molecular scale or microscopic scale. Okay. And by doing this, what will happen? We can induce some novel or some good characteristic or good property in that material. Okay, that's why. For example, you know about very much about the carbon. But when carbon is there, it's not good, right? But when we make one atomic layer of the carbon, that is called as the name is changed. That is called as one atomic layer of the carbon is called as
Graphene.
graphene. Okay. One atomic layer of the carbon is called as the graphene. And when we make bulk carbon and graphene, their properties are completely different. That's the meaning of this thing. Whatever I said here, its structure, device, or system, or we can at least tune one of the novel or superior characteristic or property. So that is called as the nanomaterial. Okay. So how we can do that? When we do at the nano scale, what happens? Nanometer is 1000 milliamps. We are always telling about the 10 raised to minus 9, right? Nanometer or some centimeter. Okay. So people are very interested in nanometer scale because at this physical and chemical properties of the materials are different compared to the bulk material. For example, when you take this carbon material, this conductivity, this resistance is very high. But when we make one atomic layer of the carbon, this conductivity increases of the order of 10. Okay, 10 raised to 10. Okay, is million times its conductivity increases. Also, resistance or physical things, mechanical property, it will increase. Okay,
Increases.
mechanical property will change. Okay. For example, when you have graphite, you can easily break that graphite by using your hand, right? But if I give you one atomic layer of the carbon, that is called as the graphene, are you able to break it by using hand?
No.
No, it's impossible because its mechanical strength is increasing. You have seen a elephant standing on a pin, right? So it means 2000s of kg that one pin can hold that weight on that graphene. So mechanical strength is increasing thousands of times. Okay, so that can bear a lot of pressure. Okay, it means that physical and chemical properties and mechanical properties or optical properties they are changing with changing the bulk material into one atomic layer. So that one atomic is done nothing but nanoscale. Okay, so what we can compare now is really what is this nanometer. Okay, so atom, we are always studying in chemistry or physics and all those things. Atom, what is atom? Atom is nothing but nucleus. It consists of the nucleus and electrons are revolving around this nucleus. Okay, so yes, yes, please don't disturb me, I'm in class. Okay, okay, this atom is nothing but a nucleus that consists of proton, neutron, and electrons are revolving around that. Okay, that depends on different materials to materials. So this dimension is about 0.1 nanometer. And if we take 1 nanometer, then DNA, our body consists of DNA, right? So this different human being have different DNA. Okay, DNA test, everybody knows about that. So dimension is how much? 1 nanometer. And now if you take the carbon nanotube or diameter, it's about 5 to 10 nanometer. Okay, so the protein, we are talking about the protein. So proteins has a dimension of about 10 nanometer. The smallest transistor that exists in the world is about 35 nanometer, and this is prepared by Feynman. Okay, so he got the Nobel Prize for that, for preparing the smallest transistor. Okay, so in our body we have a white blood cell and red blood cell. What is the dimension of the red blood cell? Is about 10 micrometer, and we have a hair also in our body. So how much dimension? About 150 micrometer. So when it comes to the micrometer scale, we can see the by naked eyes. Okay, below this, when it comes to nanometer scale, we cannot see by the naked eyes. For that, we need to use some optical device or electronic device to magnify it and see it. Okay, so that's called the optical microscope or electron microscope or scanning electron microscope, transmission electron microscope. Lot of things are there now. Okay, so one grain of the sand is about 1 millimeter. Okay, so this is just comparison. Now we can compare with the existing and non-existing things. So, for example, natural things and man-made things. Okay, so in natural things, these are the atoms of silicon. So their dimension is about less than 1 micrometer or one nanometer or something. Okay, depending on whether doping is there or not. Okay, then again we can compare with the DNA, then APT, all this. They're about 10 nanometer. Then red blood cell, we already compared this human hair. Then the stomach is about 200 micrometer. Then ant about 5 millimeter. Okay, this is natural things. But when we compare the man-made things, okay, so carbon nanotubes is about 2 nanometer. Then this is quantum coral of 48 iron atoms on copper surface. So how many of you know about this thing, quantum coral? This is the era of the artificial intelligence and machine learning. So how to induce the artificial intelligence? By using this quantum coral. Okay, so this artificial intelligence brain, this is the brain of the artificial intelligence. This is called as a quantum core. Okay, and this really controls the everything in the artificial intelligence. Okay, and this type of work was doing by my friend in Japan in 20 years back. Anirban Bandopadhyay. You can search his name, Anirban Bandopadhyay from NIMS. So he was doing all this type of the work. Okay. So this is a nanotube electrode. By using this, we can make a transistor, terminal devices. Okay. So this is about few nanometer. Then the small gearbox, okay, gears we can make by using this one, and this is about few nanometer to few micrometer thing we can do, and the head of this nail is about 1 to 2 millimeter. Okay, this is one thing. Okay, now how we can compare these things? Okay, for example, what is nanotechnology? In this one, if we take 2.5 nanometer of the DNA and we connect this thousand of this DNA, then it forms one bacteria. If we connect this thousand bacteria, then it will form the one raindrop. Okay. On the other hand, if we take 4 nanometer diameter of the nanoparticle and take 10 lakh of these grains, then it will form one ant. And if we take 10 lakh of these ants, then this will form the Indian Metropolis Speedway for the police station in the USA. That's the track. So that will form 4 kilometer of the track. If we connect 10 lakh of the ants. Okay. So if we take 1 nanometer diameter of this single wall nanotube and take 1 lakh of these nanotubes, then it will form one hair. In one hair, how many nanotubes will be there? 1 lakh. Okay. And if we connect this 1 lakh of the hairs, then you will get 10-meter wide one room of the home house. Okay. So this much small is this nanomaterial, and by using this we can do a lot of work. Okay. So research Feynman, this is the grandfather of the physics. He said in 1959, and he won the 1959 Nobel Prize for this. There is a plenty of the room at the bottom. It means that when we divide the atom into small things, okay, there are a lot of physics and chemistry or technology can be done. Okay, so there's a plenty of the room at the bottom. So he is the grandfather of this, basically this nanotechnology, but everybody neglected it. Okay, so he built an electrical motor in how much dimension? 64th part of the 1 inch cube. Okay, this is the smallest motor, electrical motor, and reduce the page of the book by a factor of 25,000. Read using the electron microscope, because naked eye is not possible, right? Because this is a nanometer scale. In 1960, Indian claimed the first prize for this one. Okay, in 1985, graduate student wrote a page from a tale of two cities in one part of the 160 millimeter in length by using the electron beam lithography. This is advanced technology in order to make very small transistor, whatever the patterning is done in our mobile and other things, they are made by the electron beam lithography. Okay, very minute contacts they are made. Okay. Okay. Now there are different approaches to make these materials. There are two approaches: bottom up and top down. Bottom up means when we have a molecule, from that molecule we have to decompose and take out the carbon and make the film of the carbon. That film of the carbon is called as a graphene. When we make one atomic layer, two atomic layer, three atomic layer, when we make the 1,000 atomic layer, then again that forms the carbon. Okay, carbon tube. Okay, so this basically when we do not have the carbon source, from the source of the molecule of that carbon we can extract the carbon and deposit on the material and make a one atomic layer of the carbon. So that is called as bottom up approach. On the other hand, you have graphite and divide that graphite to become one atomic layer. For example, you can reduce it then by using Hammer's method, or you can make a scotch tape multiple times unless and until you'll get one atomic layer of the graphene. So that is called as the top down. You have a very big atom, then divide it and make a one atomic layer. So that's called as the top down approach. You have molecule, from molecule you can make a one atomic layer. So this is called as the, for example, you have ethane, methane, or ethylene, methylene, whatever is there. By using the chemical vapor deposition, you can deposit one atomic layer of the carbon. So that is a graphene. On the other hand, you have a graphite. By that graphite, by using the scotch tape attach the Scotch tape, take out it, and again divide multiple times Scotch tape training. So that will give one atomic layer of the carbon. So that is graphene. Okay. So these are the approaches how to make a one atomic layer of the graphene. So this is zero dimension, means it's fluorine like structure. It's a buckyball like structure. This was discovered in 1985. And one atomic carbon nanotube, one dimensional carbon nanotube, this was discovered by Japanese group. Okay. So in 1991, in graphene 2004, this was plate like or thin film like thing. This was discovered in 2004, and this is graphite. Everybody knows about that one. Okay. So I'm not going in details, but the density of the state changes with the energy. This is in case of three-dimensional bulk. The energy is like this uniform or some exponential things. But in case of two-dimensional, this is staircase like quantum waves will be there. In case of one-dimensional, this is a spike-like things. Okay, density of state. But in case of quantum dot, at line like energy of the density of state will be with energy. Okay. Now, why we are using this nanomaterials and why this is very important? Because when we make nanomaterial things, its optical properties, its chemical properties, its physical properties will change. And when we measure the optical properties of the gold nanoparticles, then its emission, when we interact the light with that material, it will emit the different colors. Okay, for example, this is quantum dot of 3.2 nanometer, okay, which is blue emission. This is 3.2 nanometer. Okay, and 5 nanometer, this is red emission. Okay, material is same, but we are only changing the dimension of the material, 3.2 nanometer to 5 nanometer. This is giving the blue emission, this is giving the red emission. Means its optical properties are changing with changing the dimension of the materials. And by using this, the LEDs, colors or lot of colors can be tuned and lot of technology can be tuned. Okay. So another example of this nanotechnologies exist in a lot of natural things. Okay. For example, this is a bird. This is called as the Toucan peak. Okay. So the exterior of peak of this is made of nano-sized tiles of the keratin. Okay. These tiles is the keratin. If you use the scanning electron microscope, then you can see the layers of this keratin. Okay. They are okay. So because of this make the very rigid or rigid, a very hard thing. Okay. But interior of this peak is foam-like structure. You can see this foam-like structure made of the network of the nano-sized bone fibers. And when it hammers on some woods or something, then that can absorb the shocks and make impact on that wood. Okay, that's why you can easily make the holes in that woods. Okay, so everything is made of the nanomaterials. Okay, so another thing is butterflies. Okay, why color of the butterflies are different? Okay, we have to think about this one. Everything is matters with the light and nano technology. Okay, for example, this is blue jay. Okay, this has a color blue. Its color will not change with time. Okay, so once this color is developed, it will be remaining as a blue. So this is name itself is a blue jay. Okay, and this color is appearing because of the pigments. That's why its color will not change. When pigment is there, its color will not change, and the color of this bird is coming from the pigment. Okay, so, and this also on the nanoscience, because materials are coated on this one, and because of that, this is giving the blue color. Okay, so now I asked about the butterfly. Why butterflies has different colors? For example, the color of the beetles and butterflies' wings comes from the scattering of the light. The material which is coated on the wings of the butterflies, they are of the nanometer scale, and different butterflies have different nanomaterial. Okay, and their dimension may vary. Because of that, scattering of the light varies from different direction, and because of that, you can see the different color of the butterfly. So do you know now why these butterflies are different colors? Because different nanomaterials, different dimensions, they are coated on different butterflies, and scattering of the light on that butterflies, that gives different colors. Okay. So now you have a peacock feather. Okay. And the color of this peacock feather is not similar like the butterfly. Here, the color is because of the interference of the light, interference of the light from that nanometer scale. For example, when you put a oil drop on the water, and if you see from the different direction, it can give the different colors, right? So similarly here, the different nanoparticles coated on this peacock feather, and because of the irradiance, okay, you can see the different rainbow-like colors of the peacock feather. Okay, so first we have seen the blue jay, that is pigment. Second one, we have seen the scattering. Third one, because of the irradiance. Okay, so different nanomaterials, different phenomenon giving different colors, right? Now, this is one of the important and very interesting things. Okay, this is a fish, and it's coated with some materials underneath and bottom of this one. Okay, so this is called as a Hawaiian bobtail squid. With just two parts to process the hide from the predators at the night. First, it has a light producing organism underneath, and it produces a light because it contains the bacteria that produces luminescent light on the nanometer scale. And also, secondly, squid has the stacks of the silvery nanoparticle that is coated underneath of this one, and that reflects the light downwards, and that hides from the predictor by allowing not to form the shadow of that one. Okay, so it has the bacteria, it has the silver nanoparticles, and because of that, it has different colors, and that can produce the different colors and as well as avoid the shadow production of the shadow of that one. Okay, so now you also see this type of flies, right? This is called as fireflies. Okay, in rainy season you always see these different colors, maybe green color or yellow color or something. Okay, this always lights and off, on off is there. Okay, and this is called as the bioluminescence in the fireflies in the nanometer scale. The glow of the enzymes within that lights up, and when it off, then that electron go into the steady state. Okay, or in the stable state. And basically this happens to attract the mates or to communicate. Okay, so fireflies light is because of the enzymes. Okay, this is anglerfish. This is another interesting. In the night time, this anglerfish has this type of technology. This can light up in the night, and it can attract the fishes towards it. Okay, because of the bioluminescence, it can attract the fish and it catch the fish, and it can eat that one. Okay, so these are the examples of the nanotechnologies. Okay, so we have a lot of applications of sporting goods and all these things. Okay, so when we coat the iron with the graphene or carbon nanotubes, this is very good, and it will increase the hardness and all these things. Okay, so a lot of things are there. I'm not going to smart materials and all the things because we can change the color dimension of the materials and different things. Okay, even in the silver nano material, so the silicon solar cell and all those things, we can use the laser to make the contact like this, and it can absorb a lot of light, and it can increase the efficiency of this thing. Okay, now also in space, a lot of nanotechnology being utilized. For example, in order to store the energy, lithium ion batteries are used or fuel cells are used. And so micrometer scale and nanometer scale, the wings are coated with that one because it will increase the flexibility or hardness of that material. Also integrated aerospace engines that can give the signals, hydrogen storage, composite air cell, digital nanoelectronics. A lot of things are being applied in this space technology now. Okay. Okay. So we'll take 5 minute break, then we can start, or how you think? I'll give some example about the sodium batteries. Shall we continue, or we can take 5 minute break?
Con- Continue, sir.
I hope you are not boring. Sure,
Yes, sir.
because every human has the capacity of hearing only for 10 minutes, not more than that concentrated. Okay. So morning also I took 2 classes, then again I come and taking 2 classes. Okay, no problem. So just I will explain about the development of the batteries. Okay. So in 1800, the Holtec file, this is the copper and zinc stacking cell that is developed. This copper and alternate stacking of the copper and zinc. And by using this, we used to store the energy. Okay. In 1859, the lead acid battery was made. Okay, by using the lead and lead oxide plates. Okay, and they used to store the energy in this one. In 1899, nickel cadmium jelly roll. Basically, this is a one roll nickel and cadmium, and in between that, some jelly like things are there. By using that, we used to store the energy, but the capacity was very less, maybe zero point 0.2 or zero point 0.3 volt. Okay, in 1971, lithium iodine battery. Okay, this is not lithium ion battery. Lithium iodine battery was developed. Okay, and before that, alkaline battery like zinc, manganese oxide, cylindrical side was there. Whatever the battery we use, that is whatever battery we use, lead acid batteries, right? So we use lead and acid. The chemical reaction happens, then we have to throw out that cell. Okay, so one time reaction will happen, and once that chemicals are changed from one state to another state, then we have to throw out that one. Okay. So in 1990, okay, some companies, Asahi company and Sony company, they developed this lithium ion battery. And by using this, we can make a smallest battery that can store a lot of energy. For example, earlier our mobile was used only for 2 hours or 3 hours. Okay, maybe in 2000, 2000, 2002. Okay, but now we can use our mobile for 24 hours because the capacity of storing the energy inside that cell is increased now. Now, beyond this one, when I was in Korea in 2006, that time they also used to use mobile with foldable mobile. Now, still we do not have foldable mobiles, very small foldable mobiles, right? But that time also that mobile which has the foldable battery that was foldable. Okay, so that type of technology is there. That is called the flexible battery. If we can use a flexible battery, that we can hold it and keep it. So we have a grid to store the lot of energy, grid of the batteries. Then nanoscale battery also. For example, sometime for the working of the heart, we need a very minute type of the batteries. Okay, so for a lot of defense application, we need a very minute type of batteries. Okay, so that we can fabricate now. So the technology started in 1800. It comes to 2020 as a flexible batteries. Okay, so there are two type of batteries: primary battery and secondary battery. Now you can understand what is this. Okay, so here this consists of first thing positive and negative terminals. This positive terminal is called as anode, negative terminal is called as cathode. Okay, and this is zinc can. For example, whatever the now coatings you are drinking, that is made from aluminum can. Similar like that, this is zinc can, and in order to protect from this other things, this is a gasket. Okay, for example, whatever liquids are there, the liquids are called in the scientific terminology as the electrolytes. Okay, so in order to protect this anode from that electrolyte, we use a gasket. Okay, then zinc, then electrolyte. I already told that what is electrolyte. Electrolyte is nothing but a chemical liquid. Then carbon rod, then cathode mix. This is the another type of material. For example, sometimes we use a lead or other things. So what are the basic properties of this one? This is irreversible process. Once the chemical reactions takes place, the once ions migrate from this negative to positive, then that is permanent. That will not For example, we have a cadmium. Once it forms the cadmium oxide or cadmium to cadmium oxide, then that is dead battery. Okay, this is only one time, only oxidation or reduction. Only one process will take place there. Okay, and this has a short lifetime. For example, if you use batteries, dry batteries, okay, that will run only for 2 hours or 3 hours, not more than that. Okay, this is made up of the dry cells. Okay, this is the dry cell. What I explained is dry cell. Okay, this is cheaper. We can easily buy in 20 rupees or 30 rupees in our market. Okay, lot of companies are there. Nippon is there, then Everest is there. Lot of companies are there. So usually in small device like in torch, everybody know about torch, right? Or portable application, for example, radio or something, we we can use, or watches we can use. So can be used as long as materials are active in their compositions for the chemicals. Okay, in terms of chemicals. But in terms of these secondary ion batteries, this can be used multiple times. Charge, use, charge, discharge, again you charge it and use it. Okay, like reversible process. Oxidation reduction process that can be tuned and can be used for multiple times. Reversible and can be charged easily by electrical supply. Okay, and these are durable. You can use for example, one example is mobile. How long you can use this mobile? 3 years, 4 years, 5 years, 6 years, right? So it means the battery within that mobile is durable. Means you can multiple charge and discharge. So now we can charge and discharge for 5,000 cycles or 10,000 cycles like that. So made up of the weight cells and the molten salts. Okay, in this is one type of material. This is called the cathode. This is another type of the material. This is called as the anode. For example, this is carbon, and this is made up of sodium cobalt oxide, and this is a separator, some paraffin film, and if we uh, make some chemical liquid electrolyte in this one, then that electron will be transferred from here to here while charging, or from here to here while discharging. Okay, this is the flow of the charging and discharging. Electron will transfer from cathode to anode while charging, from anode to cathode while discharging. Okay, so multiple times this can happen. And compared to this is expensive. For example, if you want to buy this battery for the laptop, then that will, how much is the cost of the laptop battery? 5 to 6,000 rupees, right? So that is a little bit expensive. Here it's in rupees, 20 or 20 rupees, and here it's 10,000 rupees or something. Okay. So usually in large devices like inverters, automobiles, this is one of the example, and laptops or for mobiles can be used again and again by recharging it. So these type of batteries, they are made by lithium ion batteries, or we can say the sodium ion batteries. Okay. So these are recent things, okay, happening. So how this is are made? Basically, this requires the current collectors, negative and positive collectors. Then this is cathode and this is anode. In between this is separator. Okay. This metal can be changed and that can be tuned. Okay. So these electrodes are have porous in nature and help to store the large amount of the carriers. More the porosity, more storage of the charges, and that can increase the capacity of the material. So this electrode consists of the charge carriers like sodium or lithium or electrons. Okay. The separator has two electrodes because short circuiting can be avoided, and that can be used by separators. Okay. Then these current collectors may be a copper or aluminum foil that can be stacked on that, and we can collect the current. Okay. So lithium battery was first invented by this Akira Yoshino in 1885, and this was given feedback by the John Goodenough, then Whittingham, and this is Yamazi, and Kichio Mizushima. And in 1991, Sony company and Asahi company, they first made the lithium ion battery. Okay. And in 2019, Kudinap, Stanley, and Yoshino, they awarded with the Nobel Prize for this one, lithium-ion batteries. Now, whatever the batteries we are using in our mobiles, they are called as the lithium-ion batteries. Okay. So, why research on battery is needed? Because lot of things are there, lot of energy generation is there, but there is no device to store it. Okay. So, sometime we have a solar energy, but there is no device to store that solar energy. Okay. Solar energy is only available during the daytime. Okay, in order to store that, we should have the device which can store the energy. Okay, we can we cannot use lead acid batteries or something because this is primary battery. Lithium ion battery we can use. Okay, so uh, that's why we need this type of research, which material is good for storing the energy, and how its efficiency can be used, how the cyclicity can be used, and how their properties can be used. Okay, so lot of things are there. Lithium ion batteries there can be used for the transportation, for example, in the cars. Now electrical vehicles are coming down, then buses, then forklifts, automobiles. They are growing market for this one. Then in consumers electronic devices, for example, I already mentioned about few of these smartphones, laptops, tablets, and power tools and personal cares, all these things. This is one another industry. Then in energy green and industry, we are portable energy storage devices, then solar cells and windmills, then grid energy, all these things. All these needs to store the energy. Okay. For this, lithium-ion batteries are good. Okay. But this also has the limitations because lithium source is limited and geographically uneven distribution. For example, sodium sources are available in China or in Argentina or some other countries. But in India, recently they said that this is available in Kashmir, but the, still that source is very low. Okay, so in order to transport that lithium from other countries to ours, we cannot uh, transport in millions of tons at a one time because this is very expensive and very explosive. We cannot store 1 kilogram of the lithium at the one place because this is very explosive. If it attracts the moisture or temperature is very high, then because of that, explosion will happen. That will destroy everything. Okay, so transportation is not so good. Okay, the sources are limited. Only 0.02% is occurrence in the our Earth. Okay, so overheating. If we heat above 50 degrees centigrade, then your battery may explode. Okay, basically you have seen a lot of mobiles they explodes while charging or while talking. So because of fast charging, lot of time we are using that device, then that is overheating. Okay, then short lifetime they die after 1000 of times charging or discharging of the cycles. Okay, so if you want to save the energy and then you will keep your battery for ideal for longer time, but that time also that is not like the ideally 100% energy will be saved in that. If you keep your battery ideal for 2 days, then automatically the discharge will happen. After 1 month, there is no charging in that battery. Automatically that charging will die. Okay, so that's called the self discharge. Okay, then flammable. They use the chemicals that are flexible, flammable. Okay, for example, they are using the organic materials, and organic materials are always flammable, right? Right. So they are not safe to made the batteries. Okay, toxic. Lithium ion, lithium oxide, they are always toxic in nature and we cannot handle easily. So that's why we have to use the protective layers like first protective layer will be copper, then iron, then multiple casing should be there. Okay. Underperform in extreme conditions. For example, we are always using at 40 degree or 30 degrees centigrade. But when we go to Kashmir or some other low temperature area, I'm very much sure that your mobile will not work. It's dry out because the working temperature is about 10 degrees centigrade to 55 degrees centigrade. While going to very low temperature areas, please make sure that you have another type of the batteries in here. Okay. So research should take place that can operate at very low temperature, minus degree centigrade to plus 55 or 60 degrees centigrade. Okay. Then I told about the expensive casing. Because of this aluminum and copper, they are expensive, and multiple layers, aluminum casing, then copper casing should take place. These lithium ion batteries are always expensive compared to the other batteries. Expensive transport. I already mentioned that we cannot transport more than one or more than 2 kilogram of this one. Always small part we should transport it. Okay. So there's a limitation of the lithium ion batteries. So basically this cathode is, it consists of two type of anode and cathode. So this anode is lithium carbide, this graphite or something. This is one type of carbon, and another is lithium cobalt oxide, or in case of sodium, this is sodium cobalt oxide. Then electrolyte while charging and discharging. The mechanism is shown here. Okay, this is while charging and this is while discharging. Okay, I'll not go in details. I already explained this one. Okay, so what is the option to these lithium ion batteries? Because a lot of disadvantages are there, right? Limited source, overheating, short lifetime, self discharge, flammable, a lot of things are there. So how to overcome this? So for that, sodium ion batteries is the best option. Why? Because this is earth abundant element. How this is earth abundant element? What is the source of this sodium? Anyone? Am I audible to you? Am I audible? Okay. So, okay, sodium chloride that is present in the seawater. Okay. From seawater, we can make electrolysis and extract the sodium from that. Okay. And we can utilize for our batteries. Okay. So that is earth abundant, and it's a lot of seawater is there. We can utilize that one. Okay. Then that is easily available from the seawater, and this can be a powerful anode and can produce from ignite or some lot of things, and we can make a biomass, and biomass can be made into carbon, and that carbon can be utilized as one of the material cathode or anode. Okay. Then how about the performance? We have to compare the performance with the lithium ion batteries. We cannot compromise that, right? While applications. So when we use sodium ion batteries and lithium ion batteries, the performance given by the sodium battery should be comparable. Okay. So this is sodium ion versus lithium ion batteries. Okay. So this blue is nothing but this sodium ion, and this other is green is nothing but lithium ion batteries. Okay. So we can see in cost wise, 30% less cost than lithium ion batteries, because the current collector and the casing required for the sodium ion batteries is cheaper. Also, the abundance of the sodium is much more higher than the lithium. Lithium occurrence is 0.02%. Here, a lot of things are there, 20% or more than that. Okay, 2%. Okay, that salt is available. Then energy density. Energy density means how much the capacity to store that energy. For example, when we buy the mobile, what do you see about the battery? Milliampere hour, right? Milliampere hour. So that is the energy density. Okay. So that should be comparable. Both are almost equivalent. No difference in that one. Also, the operating temperature, I told that if you use this lithium ion batteries in the very low temperature, for example, Kashmir or other things, or some other countries, Canada, Canada, okay. So there, they are not performing good. So here, if we use sodium ion batteries, then operation temperature is changing from 10 degrees centigrade to minus 20 degrees centigrade. So the operating temperature automatically changing. The higher temperature also is 55 to 60 degrees centigrade. So this is much more beneficial, better, right? This is better than the lithium-ion batteries. Life cycle. This is still there is some studies going on, but this is comparable, not less. It's almost comparable with the lithium-ion batteries. So this is carried on one of the company which make the sodium-ion batteries. Okay. So safety. This is 25% more enhanced safety, and we can charge and discharge to 0 volt. Okay. Now I will ask one question. Can you discharge your battery, mobile battery to 0 volt? If you discharge your battery to 0 volt, then you have to forget about the battery. Okay. Because all the metals that is accumulated in the form of the lithium. Okay. And that will explode anytime. So please do not discharge your battery less than 10% or 5%. Okay. If you discharge that, there is very problematic for you. Okay. And also, while charging your mobile, not charge more than 80%. Okay. Because that is fully charged, then again that is very difficult to control the ions in that material. Okay. So again, discharging and charging of your lithium-ion batteries, whatever presented things, that should not be less than 5% and not more than 85%. Okay, that is the limit. But in case of sodium-ion batteries, you can go to 0 volt also. Okay, fully discharged, fully charged. Okay, this is possible. So 20% enhanced safety is available in case of sodium-ion batteries. Okay, higher availability of the sodium makes it very easy to utilize for the sodium batteries. For example, this is 0.002% per million. This is 2.36% per million, and this is cheaper than the lithium. And there are a lot of things we can I will compare this one. Okay, so I will briefly give about the outline of the. This is zinc oxide nanostructure. Hope you are not boring. How much time I have? Okay, fine. Hope nobody is boring. It should not be typical research work or something. Okay. Okay. So basically, I will explain this in 10 or 15 minutes about the zinc oxide and zinc oxide, how to make the zinc oxide in your lab, and how to characterize it, and how to bring into application. Okay. You can note down, and you can within a day you can make this one. Okay, in your lab. Okay. So whatever chemicals required for this, I will tell. What first? Why zinc oxide? Because zinc oxide has a direct band gap of the semiconductor. Direct band gap means conduction band and valence band. They are peak of the conduction and valence band. They are each above. Okay. So electron can directly go from valence band to conduction band. Okay. So that's why that's called the direct band gap, right? So wide band gap means if the this band gap is more than 3 electron volts, up to 6 electron volt, that is called the wide band gap semiconductor. If it's less than 3 electron volt, then that is called the narrow band gap semiconductors. And when we want to utilize this material for some applications, the melting point should be very high. For example, we want to generate the source of the electrons, then we want to get that electron. Before that, it will melt. So there is no source of the electrons. Before that, it will melt. But in case of zinc oxide, this melting point is very high, about 2000 degrees centigrade. Okay. And this is naturally n-type. Majority of the carriers will be electrons. And mobility is about 2000 centimeters square per volt second. Mobility is nothing but when you apply the 1 volt of the potential to that, it will travel 2000 centimeters square in 1 second. So that's called the mobilities. So it's very high mobility of the zinc. Okay. So we are widely used in many things in laser, LEDs, all these things, but I will not go in details of that one. Also in sensors and solar cell applications. For example, one example I will tell about the sun cream. Okay. Why you use sun cream? In order to protect from the IR radiation. Okay. When IR radiation interact with our body, it forms the burning. That burning is nothing but that is creating the nucleus of the cancer. Okay. In order to protect the direct interaction of the IR with our sorry UV okay UV with our body, we have to use the lotion so that it can absorb and it can reflect. Okay. So zinc oxide and titanium oxide, they are very good materials for this purpose. Okay. So most of the sunscreen, they are using this one. So there are a lot of techniques we can utilize to prepare this zinc oxide. For example, chemical vapor deposition, physical vapor deposition. This chemical vapor deposition, we can use a tube, and that tube can be winded with electrical wiring, and that can be heated, and we can make a thin film. In physical vapor deposition, we can use pulse laser deposition or some other sputtering techniques, or electro deposition, hydrothermal method, or sol gel method, or wet chemical method. So I will talk about the wet chemical method. What is this wet chemical method? So what are the parameters and how to tune them? And if we tune them, then what will happen? Okay, this is simple example. This was carried out in 2014 by one of my student. Okay, so starting with zinc oxide precursor, you can take the zinc nitrate or zinc acetate and dissolve in water by different concentration, and maintain the basic by adding ammonia solution or some NaOH solution. And if you heat it at particular temperature, about 80 degree to 90 degree or 100 degree centigrade, then you will get the zinc oxide powder. Okay, nano powder, nano crystal powder. So here, how much concentration we are taking, how much the concentration of zinc nitrate, or how much temperature we are heating, at which temperature we are preparing the materials, at 80 degree or 90 degree or 100 degree. Okay, and how much time we are holding? Only 30 minutes, 1 hour, 2 hour, or more than that. Okay, or we are doping anything materials. For example, we are replacing zinc with other materials. That is also very important. Okay, so there are different parameters. If we tune this, then what will happen? For example, I will talk about the concentration changing, then temperature changing, then time, then doping. Not all at a time, one by one parameter we need to change to study the effect of this. Okay. For example, if I keep the temperature about 100 degrees centigrade and time for 120 minute constant, okay, and if we change the concentration from 50 millimolar to 250 millimolar, then you can see this needle like morphology. You can see it on microscope. It will change to tapered needle like structure. Okay, its dimension also increasing. Okay, so it means that if we keep the temperature constant and time constant and changing the concentration, then its morphology is changing. Okay, then if we keep the constant time about 2 hour and concentration about 100 millimolar, and we change the preparation temperature, like prepare at 70 degrees centigrade, 90 degrees centigrade, 120 degrees centigrade, then you can see this needle like morphology formed at 70 degrees centigrade and 90 degrees centigrade. This is forming the rod-like structure, and at 100 degrees centigrade, completely rod-like structure, and 120 degrees centigrade, this is a tube-like structure. Okay, so we are keeping the same thing, the same batch, but we are changing the different, preparing at different temperatures, 70 degrees centigrade to 120 degrees centigrade. This is forming the needle-like structure, rod-like structure, then tube-like structure. It means that preparation temperature is very also important, that play a crucial role in the controlling the nanometer scale of these zinc oxides. Now, I prepared two set of the things. Okay, this is first uh, 330 to 120 minute by at 70 degrees centigrade, and this is prepared at 120 degrees centigrade, and concentration is same, 100 millimolar. Okay, so you can see that this is needle-like structure is remaining needle-like structure, but dimension is increasing. Rod-like structure changing from 30 minute to tube-like structure at 120 minute. So the duration of the preparation of the material is also very important. You have to stop the reaction at the particular time, so we can get the important thing. Now, I prepared the material, but why I'm getting this rod-like structure or needle-like structure? Basically, the growth mechanism we have to study. Okay, for this, in case of this needle-like structure, screw dislocation is playing the important role, and because of that, its growth along c-axis direction is much more higher than compared to other direction, and that's why we're getting the needle-like structure. But in case of this rod-like structure, layer by layer, its deposition is from side by side. That's why we're getting the rod-like structure. Okay. Now we have prepared the material. Now we have to characterize the material and is there any change in the material? Okay. The first important technique that can give the information about the phase period is that XRD. If we compare with the standard XRD pattern, then all the peaks that should match SKL parameters that should match with the standard parameters. Okay. So if any extra peak is appearing, that is nothing but impurity. Okay. So in case of this strontium doping and nickel doping, you can see this strontium doping. This is black. Then this is 4%. This is 8%. This is green. Okay. This 2 theta is changing to lower 2 theta. It means lattice constant is increasing. It means with doping of zinc with strontium, the lattice parameter is increasing. Okay. And that reflect from this XRD. Okay. In case of nickel, first is going down lower angle, then going to higher angle. And here the mechanism is not so easy. Here the surface morphology is maybe changing because of that strain is increasing or strain is decreasing. That's why that's constant is decreasing. Basically, when we replace the small ionic radii with higher ionic radii, the lattice constant should increase. For example, we are replacing 0.74 angstrom with strontium, then automatically this small ball is replaced by higher ball. Okay, then lattice constant should increase because the unit cell is increasing. Okay, that is happening here. But in case of nickel, we are replacing 0.74 angstrom with 0.7969 angstrom. Then that is expected that lattice constant should decrease. Okay, replacing higher ball with smaller ionic balls. Okay, but here this mechanism not so simple because the strain is playing role here. So okay, and that can reflect from this morphology studies. Okay, this rod-like structure is becoming the plate-like structure. This is intermediate state. Okay, you can really see that this rod-like structure, they are becoming two rod-like structure, and that plate is connecting, and it become the completely plate-like structure. Okay, now we need to study the another properties, like what is the optical property of this one, or what is the um, doping intensity, or what is the concentration of doping, whether that will change the optical properties of that one. Okay, or defect level is changing, that can be studied by photoluminescence studies. Okay, so if we keep the normalize the intensity of the green light and compare the intensity of the UV light of these different dope things, this intensity is continuously decreasing. It means that the doping concentration is changing with changing the doping of the strontium and nickel. Okay, so this is very important. So we got two different things now. The change in the morphology is going on, this change in the defect level is going on, whether we can utilize this for the different applications. Okay, defects are very useful for the sensing applications and optical applications. Then change in the morphology with enhanced surface area is useful for the supercapacitor applications. For example, zinc oxide rods have surface area 4.35 meters square per gram. And when we dope with 12%, then it will increase the surface area from 4.35 to 51.44. 10 times higher surface area we are getting. And I already mentioned that rod-like structure is changing to flower-like structure in case of nickel. Okay. So first I told about the how to prepare the material. Then what I told, how to characterize the material by using XRD, SEM, photoluminescence. Okay. Now some applications I will give about this zinc oxide nanostructures. I have tested for different applications, zinc oxide for gas sensing application, then field emission. I told about the source of the electron can be generated by using this one. So we were generated this electron source, and that can be utilized for the scanning electron microscope, transmitting electron microscope. Then diode semiconductors, to photon observation, for example, laser applications. Then energy storage applications, supercapacitor applications. So first application is solar, this supercapacitor application, and that can be measured by using this cyclic photometry. And this is 15% nickel doped zinc oxide, and you can really see that earlier this nickel oxide, when nickel was doped at zinc, it was rod-like structure. At 15% of the doping, atomic percent doping, is completely tower-like structure. And when we measure the specific capacity of this one at different scan rate, we can see maximum of 600 Faraday per gram of the this material. Okay, so that you can easily calculate by using this. Lot of sources available. Maybe other people also talked about this, how to calculate this one. I will not go in details of that one. Another thing is that by charging and discharging time, we can easily calculate the specific capacitance, and that is also giving the more than 600 Faraday per gram. Okay, so it means that this material is very potential, but compared with other material, other people's work, where we are standing, so other people's work maximum space capacitance is 317, but because of the controlled morphology and properties, we are getting about 700 Faraday per gram, almost double of that one. Okay, so it means that our work is potential for application, and this is a pulse cell supercapacitor prepared in our lab. Okay, one of the student, Dr. Pratik Bhojne, he have prepared this one, and this charged for 10 seconds, and it can light up this LED. Okay, so now sensors, CO2 and CO2 sensor, CO and CO2 are very toxic gases, and if we can inhale 50 part per million of this CO or 5,000 part per million of the CO2 for 8 hours inhalation in our body, then we can meet the death. Okay, so these are the limits given by the OSHA, that is Occupational Safety and Health Organization, the USA organization. And in order to detect this one, metal oxides are very important, and they are very high sensitive, low power consumption, lower price, quick response. I'll tell about what is this quick response or something. When we expose, for example, this is the baseline, and when we expose the gas to this material, then that should give a sudden fall in the resistance or capacity of the things. Okay, and that is called as response time. And recovery time means when we stop the flowing of the that gas, then it should come to the original state within short time. That's called the recovery time. Okay, so this response time and recovery time, they're very important, and this is showing that the exposure of the 5 per million or 80 part per million, this change in the resistance is systematic, and by using this we can calculate the calibration curve, and by using this calibration curve, the minimum amount of the CO2 that can detect by using this nickel doped zinc oxide sensor is about 2 part per million. Okay, on the other hand, if we dope with strontium, this is good for the CO2 sensor, and it can detect about 25% of the CO2. Okay, so this is also good. Okay, so another important property is that our sensor is working out about 250 degrees centigrade. Other sensors are they working about 300 degrees centigrade. Okay, and our response and recovery time are very small, 5 seconds, and their capacity is also very good. Okay, so this is our interesting work. Now, generation of electron source that I mentioned about melting point and all these things, because of high melting point of zinc oxide, we can use this, and we can generate the X-ray and electron source and flat. For example, whatever the flat displays are there, they are using this electron source, and transmission electron microscopy is one of the application of this one. And just in comparison, this is the zinc oxide, and when we dope with the nickel or zinc oxide, then the electron source is generated at lower voltage, and that can be potential for the source of the electrons in the whatever electron transmission or scanning electron microscopy, we can utilize this one. Okay, so this is another important property. So two photon observation. Many people you don't know. Also, I will not go into much of the details of this one. When we use the pure zinc oxide, and this is 10% zinc oxide, two photon observation, that uh, constant is increasing 14 times. Means the lasing action in this material is increasing. Okay, so this material was used for the nano lasing of my material is used for nano lasing. So lasers are being generated by using this material. So this two photon observation gives the applications for the laser application where it utilize or not. So that application is being carried out. Okay. So in summary, zinc oxide and structured materials are synthesized successfully by wet chemical method. And I explained about the characterization by using XRD, SCM, then photoluminescence, and few applications. For example, supercapacitor, then two photon observation. Okay, all these things I have explained. Okay, and if you have any queries or something, then you are free to ask me. Thank you very much. No questions? It means you don't understand, or grasping is not so good, or my teaching is not so good.
No, sir, that is not. Session is nice.
Sir,
Hello?
There are two persons. One is Sharad Chand.
sir, you have, thank you, sir. Sir, you have given the advantages of use semiconductor somewhere in that train. What do you call it? Super fast train.
It's
Okay.
not semiconductor, it's superconductor.
Superconductor, sorry.
Yes.
What are the disadvantages of that?
Disadvantage is that they are superconductor at very low temperature, liquid helium or liquid nitrogen range. Okay. So we have to make them room temperature superconductor. Then that is really advantageous. Now they are disadvantages because lot of price we are utilizing for cooling down that material.
Okay. Okay.
So controlling, for example, in superconductor, in normal metal we can use maybe 1 ampere of the current, but in case of superconductor, we can pass mega ampere of the current. Okay,
Hmm.
so that can sustain. And whatever the large magnets they are producing, they are using superconductors.
Okay.
Madam, sound is not clear.
I,
Noise is generated.
for others, am I clear?
Yes, sir.
Okay, huh. Recycling of batteries, still that process is in process. Okay, but not really lithium ion batteries or something is being reprocessed. Okay, because when we open that lithium, it interact with the air and that exports. Okay, so that is not so good. On the other hand, in this lithium ion batteries, we are not really using the lithium metals. When we use the intermediate charging, then that is converted into alloys. Okay, that's a little bit safer than other things. Okay, so we can use that for recycling, but the process of the recycling is not yet established.
Sir, is there any process to separate out pure lithium from that cells?
Yeah, that
Is
is
there any
possible,
research?
but the process is very expensive. For example, electrolysis is always there,
Yes, sir.
but rather than electrolysis, that is very expensive, right? You can buy the pure material and you can utilize for applications.
Sodium ion battery, sir.
Both are the same. Once you make the alloys, then it's very difficult to take out or recycle it.
So then what is the future of lithium ion cells?
Lithium still exists, but now it's time to get rid of the lithium because source is very less and they're really expensive. So lithium can be replaced with the sodium. That is much more cheaper, right? 30% cheaper because sodium is easily available.
Yes, sir.
So other techniques also being utilized to convert sodium chloride into sodium.
Okay. Okay, sir.
I think everyone is
सर
tired.
सर
Yes, yes,
सर
Pawan.
आपने केवल सुपर कंडक्टर के एडवांटेज के बारे में बताया, उसके मेंटेनेंस और डिसएडवांटेज के बारे में नहीं बताया।
हाँ, अभी मैंने शायद लगता है कि बताया अभी मैंने, है ना। उस उसको मेंटेन करने के लिए हमें बहुत लो टेम्परेचर लगता है, लिक्विड हीलियम और लिक्विड नाइट्रोजन, and coolant of this is very very expensive. Okay, and when after few days that coolant will be overrated, so always we need to fill that with liquid helium or liquid nitrogen tank. Okay, and liquid helium is very very expensive,
यस सर।
so economy is very high in case of superconductor. Any other questions? Thank you, thank you very much. Okay, bye bye.